Please be seated. We'll get started with our first session of the day. So I'm Dick Plambeck, the session chair, and I'm pleased to introduce Tom Troland as our first speaker, who will be telling us about Zeeman effect measurements in the ISM, past, present, and future.
That's a triple whammy. Thank you, Dick. Good morning. Welcome to day 3 of Crutcher Heiles Fest. I hope you're all bright-eyed, bushy-tailed, ready for another day of action astrophysics. Hope nobody overindulged on food or drink last night. And again, I also hope no one underindulged. That's another mistake. What I'd like to do today is talk a little bit about the Zeeman effect, which is altogether fitting and proper given the 2 honorees of this conference. And the story begins over 2,000 years ago with a fellow named Thales, who supposedly was the first person to note and describe the lodestone, the magnetic naturally occurring rock. And then if we move further ahead in time by several millennia, we reach the epoch of a fellow named Stokes, who had some parameters named after him. That's also relevant to this story. Then we move into slightly further ahead in time to a guy named Zeeman, who has an effect named after him. And then finally, of course, we reach the modern epoch with Carl Heiles and Dick Crutcher. Both Carl and Dick have clouds named after them. Carl's clouds are kind of small. Dick has a very large cloud named after him, so I don't know if that makes a difference. One of the things I was reflecting on as I was walking here today is the fact that I feel a bit of a failure as a scientist, because there's nothing named after me. There are no parameters, there are no clouds, no effects, not even a hole. Jay Lockman here has a hole named after him, and that's, I'd go even with that. I started to think that I guess my preference would be to have an effect, the Troland effect, because then you could have the inverse Troland effect and even the relativistic Troland effect, but I don't know that that's going to happen. Anyway, speaking of effects, we're here to talk about the Zeeman effect, so let me tell you a little bit about the Zeeman effect. Now, I realize that many in this audience know very well the Zeeman effect, so you're not going to learn so much about from parts of this talk. Others are somewhat familiar with the Zeeman effect, but not everyone in this group is a Zeemanologist, so please bear with me if you are. Let's start with the advantages of the Zeeman effect. It's always nice to start on a positive note. The Zeeman effect is the only effect in physics that we have so far that allows us to measure the magnetic field strength in localized regions of the interstellar medium. And in that sense, it's very, very useful. There are other ways of estimating the magnetic field strength based on various indirect parameters, and that's helpful, of course, but with the Zeeman effect, we can measure it directly, in principle. It's also useful that the Zeeman effect can be detected in a variety of locations, both in absorption and emission in radio frequency spectral lines, so we can sample a variety of regimes of column density, volume density, and other types of regions. So that's all good, but of course there's some limitations, and these are known to anyone in the Zeemanology field, as well as, of course, many others who are not. The Zeeman effect is only a measure of one component of the magnetic field, the line of sight component only, with very rare exceptions. It only can be used to study the magnetic field based on spectral lines from a few species, such as H1, OH, and CN. And it involves the measurement of very weak circular polarization, so it's very, very sensitivity limited. In some cases, we have spent 50 hours observing a single position to get a Zeeman effect detection. In fact, we may have spent 50 hours and gotten nothing. I don't remember for sure. There are instrumental effects as well. I won't go into the details, but I will mention them briefly because they are a real constraint when it comes to matters of Zeeman effect measurements. Now, since its discovery in 1968, and I'll briefly detail some of the history of the Zeeman effect. Since its discovery in 1968, the two leaders in Zeeman effect studies are the 2 people we are honoring here today, Carl Heiles and Dick Crutcher. Carl Heiles has led the way in Zeeman effect observations of the diffuse gas, and Dick Crutcher has led the way in Zeeman effect measurements of molecular gas. virtually every idea of importance, I can't overemphasize this, virtually every idea of importance that has to do with measurement of the Zeeman effect over a wide range of astrophysical environments. Those ideas, almost all of them, have come from Carl Heiles and Dick Crutcher. Now, there have been some other people involved, of course, and here you see several others who are here, and more beyond this as well, of course, but Carl and Dick really, again, have been the leaders in this field. So let's talk briefly about the history of the Zeeman effect. I won't spend too much time on this because I'm not a historian and this is not a history conference, but in any case, it was discovered, as I'm sure most of you know, in the late 1960s by Gerrit Verschuur. And you see the paper there, which he published, announcing the first discovery of the magnetic field in H1 absorption lines towards Cas-A. I recently discovered from a source that Gerrit Verschuur currently believes that no other Zeeman effect detection, except the one that he published in 1969, is correct. So you may be wasting your time sitting here and listening to me talk about these things. I'll leave that for you to judge. After the Zeeman effect was detected, Carl Heiles had the idea in the early 1970s that this would be an effect that one could observe in the H1 sky, and with the 85-foot telescope, he set about to do so. I was at that time a young graduate student working with him, so I was obviously part of that project. And it took a little while. We started in the early 70s. It wasn't until the early 80s, almost a decade later, that we were successful. Took a long time. That's why I claim I took 10 years to complete my degree, because of the difficulty of this. Actually, it's probably more because I'm a procrastinator. But anyway, it's also worth noting, perhaps only for me, perhaps I have a daughter who is 40% smarter than I am because she got her PhD in another field in only 6 years. It took her old man 10. Anyway, that's, I guess, evolution. People get smarter as time goes on. The idea was to sample the warm neutral medium by studying H1 in emission, and we did eventually succeed in doing that, although there were numerous problems along the way. This was the biggest problem of all, although this didn't directly affect me. Carl continued the project after I left Berkeley in 1980 and gathered more data of the Zeeman effect in H1 emission lines. And then the telescope, of course, was lost. We will learn today from Carl about further results from this project, which took place so long ago. Then moving on in Zeeman history, the first detection of the Zeeman effect in OH occurred thanks to the efforts of Dick Crutcher and his colleague Elia Cassis. Dick mentioned this briefly in his presentation yesterday, published in 1983, detection of the OH absorption Zeeman effect. This now resulted in the sampling by the Zeeman effect of a different regime rather than the warm neutral medium, now sampling molecular gas associated with H2 regions, because the H2 regions or H plus regions were providing the radio continuum against which the absorption lines occurred. The first detection of the Zeeman effect in emission occurred, as Dick said yesterday, at Arecibo in 1989. Alyssa Goodman was a graduate student at that time and was key to that project, and others were involved in it, myself as well, for that matter. Here now we were sampling for the first time gas in molecular cores, however we define cores. Back in those days, we had a somewhat simpler perspective on such matters than we do today, but in any case, it was a new detection and an important one, and it was continued with further observations both at Arecibo and at Greenbank to increase the number of OH emission line Zeeman effect observations that were made, and therefore the number of cores that were sampled in that way. Also, an important project was undertaken by another group. Tyler Bork and Phil Myers pursued the Zeeman effect in OH absorption lines towards galactic H plus regions and published a paper in 2001 with a lot of results. A real advance in the Zeeman business came as a result of Dick Crutcher's insight. Dick had the idea, and he mentioned this briefly yesterday, of trying to observe the Zeeman effect in the CN lines. And that was a really important thing to do because the CN lines now sample a much denser regime of gas than could be sampled then by OH, much less, of course, H1. And so that project began in the mid-1990s and continued, leading to the first detection reported in 1999. And subsequent to that time, there's been a lot of work done by Dick and by Edith Valgaron, who is here, who has been a key player in the CN Zeeman campaign. And we have detected a number of other sources. There was a paper in 2008 that listed the detections and discussed the detections at that time, and we continue to work on that project. Just a few other moments in the history of the Zeeman effect. The Zeeman effect was also detected. Oh, hey, I already have that one. I think I talked about that. The Tyler Bork and company. Oh, I went backwards, sorry. There you go. Okay, here we are now. Wrong button. It's funny how something can go wrong if you push the wrong button. When Donald Trump becomes president, obviously, he'll hopefully not push the wrong button. It could be a problem. Anyway, that would not be terrific, believe me. The Millennium Survey, then, you've heard something about this. Most people. Sorry? His fingers are too short. You know, let's not go to that type of joke, please. Here at a meeting like this, I see. Okay, good one though. I like that. Carl's graduate students sometimes have a slightly off-color sense of humor. I'm not sure where that comes from, but anyway. The Millennium Survey, you know about that. That was a project conceived by Carl, executed by Carl with a lot of help from me, but in any case, resulted in detection of the Zeeman effect in cold neutral medium by studying H1 and absorption towards background continuum sources. And then that project was then followed by another similar project, a related project, Zeeman effect in OHO Mission, where we chose extragalactic sources, a long way away, of course, that lay behind molecular clouds. And those extragalactic sources then probed the peripheries of molecular clouds, an idea which actually originally came from Chris McKee. Somewhat less well known, and I won't dwell on it, but interesting series of observations that span over a number of years involving Carl and Dick and myself, observations of the Zeeman effect in OH and H1 absorption towards galactic H2 regions, and using aperture synthesis techniques, you can actually map the line of sight magnetic field across the source. And I'll talk a little bit about an application of that to the Orion Nebula in a talk I'm giving on Friday. Just to briefly cite some other people involved in this effort over the years, this is not a complete list by any means. Tim Robershaw has a complete list, but some of the people whose names have not appeared already but have played key roles in the Zeeman effect are listed there. Okay, let's talk briefly about something that is a complex subject, and I won't go through it in any detail because very few of you here would be interested in knowing the details. It's something called instrumental circular polarization. It's a key problem in Zeeman effect measurements. And the basic idea is that in order to measure the Zeeman effect, we have to measure the Stokes parameter V, that is to say the difference between right and left circular polarization. The problem is that the telescope responds typically somewhat differently in right and left circular polarization. So when you observe a spectral line in right and then observe it in left and take the difference, what's left over is not just the result of the Zeeman effect in the sky, but it can also be the result of differences in the telescope response pattern in left and right circular polarization. And this contribution from the instrument is known as instrumental circular polarization. Let me just give you a brief example. Dick Crutcher talked about this also in his presentation yesterday. Here you see two telescope beams in Arecibo observed by Heiles and collaborators about a little more than a decade ago. On the left, you see the Stokes I-beam, that is to say the regular telescope beam, the sum of the two orthogonal polarizations, and you see the main beam and some side lobes. On the right, you see the Stokes V-beam, the difference between right and left circular polarized beams, and of course it's not zero. The black area is positive, the white area is negative, and that type of pattern in the Stokes V-beam, which you see on the right of the screen, that type of pattern really amounts to, as Dick said yesterday, a small offset in position between the telescope beam and right and left circular polarization, which means that when you are switching between right and left circular polarization, you're also switching position in the sky. It's a small fraction of the total beam width, but still it's an important effect, and it's something that can create an instrumental Zeeman effect. Because if the spectral line source, as Dick said yesterday, has a velocity gradient and hence a frequency gradient, then this offset in position of the two telescope beams can interact with that change with position of the frequency or velocity of the line in such a way as to create a false Zeeman effect. So that's especially dangerous, and that's something that Zeeman observers are always on guard for. It gets worse than that, though, in some cases, because the telescope beam not only has responses near its beam center, but also over a wide solid angle away from the beam center. This is a map, this windmill type map that you see here was one I made in collaboration with Carl back when I was in graduate school, published in '82. It shows the Stokes V beam out to 12 degrees away from beam center, a total range of 24 degrees. And you can see that the telescope responds weakly, but quite differently in the two circular polarizations over a wide range of angle in the sky. And since H1 emission is also, of course, distributed all over the sky, this far out side lobe effect is one which is very dangerous, especially for H1 emission observations. And that's the problem. I bring this up in part because that's the problem with the GBT. The GBT is a wonderful instrument. It's been a great pleasure using the GBT. It's just fabulous. But it does have significant far outside lobes that are associated with the Cassegrain design and the illumination of the Cassegrain secondary by the feed of the telescope. All these are described by Robichaud and Heiles in 2009. And the net effect is that the GBT is not a good instrument to use for H1 Zeeman emission observations. There may be ways to get around some of these problems, but it will be and has been very difficult. Let's take a look now at where we stand in terms of Zeeman observations, Zeeman present, you might say. Here's a table that shows the three principal Zeeman species, in fact, the only ones so far that have been successfully used for the Zeeman effect, H1, OH, and CN. Fortunately, these three different species do sample a wide range of volume density and hence column density, column density. And so we're at a point now, after many decades of Zeeman observations, assuming, of course, that they're not all in error, except the very first one that Verschure, of course, reported. We're in a position now where we do have a somewhat statistically valid, depending on how you define such things, data set. It's taken many, many years, and this table shows the principal published Zeeman data sets that are out there. This table, in some sense, encapsulates much of the career of Carl Heiles and Dick Crutcher, and also me. Our efforts and the efforts of a number of collaborators, such as Edith Valgaron and others, have led ultimately to this data set. And we have a number of results, and that's the fruit of this labor, and I think it's made it all worthwhile. There is another data set which I'll include and which I've discussed in a number of conferences over the years and need to get published. That's my plan this coming summer. The Arecibo OH absorption survey done with my graduate student Kristen Thompson, former graduate student. She's now a faculty member at a school in North Carolina. This is where, as I mentioned earlier, we observed the OH Zeeman effect in absorption lines against extragalactic continuum sources. And the idea, again, one that Chris McKee originally suggested, was to probe lines of sight, not just in molecular cores in GMCs, but just random lines of sight that were defined by the locations of these background sources. So this is a way of probing magnetic fields in GMCs at large. Now, just let me review a few things that are very, 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 very well known to so many of you in this group, but if you're not a Zeemanologist or magnetologist or cosmetologist or whatever, then this might be something of some value. There's this concept of mass to flux ratio, and it is essentially the ratio of gravitation. It is the ratio of gravitational to magnetic energy in a cloud. There's a critical mass to flux ratio, which corresponds to the situation where the gravitational and magnetic energies are equal. And we can define, as you see here, a normalized mass to flux ratio, which is the ratio of the actual mass to flux ratio in a cloud to the critical value, and that is the square root of the ratio of the gravitational to the magnetic energy. So this parameter is a parameter that can be directly measured through Zeeman effect observations, and it's very important to the evolution of clouds. There are two possibilities if we consider this parameter lambda, the normalized mass to flux ratio. The weak field case is a case where gravity dominates the magnetic field. Such a cloud is said to be magnetically supercritical, and in such a case, the magnetic field is not capable of preventing the star, or the cloud rather, from collapsing. The opposite case is where lambda, for some reason, lambda doesn't show here. Okay, oddly enough. I don't know why that is, but anyway, if lambda is less than 1, Funny how these fonts go. That's the strong field case where the magnetic field dominates and where the magnetic field will keep the cloud from collapsing forever as long as flux freezing is maintained. So let me move on to the results, and I'll show you this diagram similar to the one that Dick Crutcher showed, and also having been shown a number of places and published as well. For each Zeeman effect measurement that we can make, we have, of course, the line of sight magnetic field, and then also we can estimate the column density using the characteristics of the same spectral line that was used for the Zeeman observation. So the net body of data on Zeeman effect observations includes now a fairly large number of measurements of magnetic field strength, line of sight magnetic field strength, and the column densities to which those magnetic field strength measurements are applicable. And here now is this diagram very similar to the one Dick showed with a few more data points shown. This is it. This is all we have right now. This is the result of about 30 years of work. And so you better like it. If you don't, then heck with you. Many of you have seen this already, probably. Wonder why I'm showing it again. Well, I'm just going to do that anyway. Let me just walk you through this a little bit, even though this has happened already and many of you are very familiar with it. The red data points, as you see there, are the ones for this more recent and not yet published survey of OH absorption towards extragalactic continuum sources probing the peripheries, that is to say, generally the non-cores of molecular clouds. So it kind of fills in some of the other data points that you see there. I show here the fact that this range of column density is one in which different probes are used. The lower column density regions are the ones that have been probed by H1, intermediate column densities probed by OH, and the highest column densities, and also highest volume densities probed by the CN, Zeeman effect. We can also consider the value of lambda in, this is really annoying. The lambda character has simply disappeared from this presentation, but anyway, use your imaginations, it's very important. If lambda is less than 1, that's the regime in the upper left. The blue line there, the diagonal blue line, is the line which separates, it's the line, it's the locus of lambda equals 1, and it separates the magnetically dominated subcritical region in the upper left from the gravitationally dominated supercritical region in the lower right. Also, we can label the same diagram. I'm showing the same diagram over and over, just labeled somewhat differently. To the left, you see the cold neutral medium. In the middle, you see molecular cloud peripheries from OH absorption, and then to the right, you see molecular cloud cores from a combination of OH Zeeman observations and CN Zeeman observations. So let's go through some conclusions we can draw from this diagram in the few more minutes we have here. As you look at this diagram, and this has been widely commented upon before, you look at this diagram for low column densities, namely the column densities associated with the diffuse gas, the material is magnetically subcritical. That is to say, it is magnetically dominated. This is not surprising, of course, because this diffuse gas has very little in the way of gravitation. It's not self-gravitating gas. Not surprising, perhaps, that the magnetic field would be dominant. So the low column density, less than 10 to the 21 column density gas that's been sampled so far, which is diffuse cold neutral medium, sampled by the H1 Zeeman effect and absorption, is magnetically subcritical, magnetically dominated. So that's one point we can make. As we move up in column density, particularly to the regions within giant molecular clouds that are sampled by the OH absorption Zeeman effect, this molecular cloud peripheries, as I call them, the red dots, now we move into a regime where the gas is magnetically critical, very close to lambda equals 1. And if we move up in column density, or actually if we include a wider range of column density, then perhaps in some senses the most obvious conclusion you can draw from these data is that there is a wide range of column density over which the magnetic field doesn't appear to change at all. That's something that indeed has been known, of course, for a very long time. As you move from low column density to higher column density on that right-hand side of the diagram, since the magnetic field is remaining constant while the column density is increasing, that means, of course, that lambda is increasing as a function of column density. Oh, hey, lambda is there. That's interesting. Well, the mystery of the lambda. Even though I was in a fraternity and went to an actual toga party years ago at the fraternity, I still don't understand Greek letters very well. So I don't understand them here in a presentation. So for low column density, by this case, we mean up to about 10 to the 22, as you can see there, the value of lambda increases. And then when we get to column densities of 10 to the 22 and greater, you see the magnetic field strength starting to increase. And at that point, with B rising in proportion to the column density, the value of lambda reaches a sort of semi-constant value of maybe 2 to 4 times critical, which is to say molecular cores are mildly magnetically supercritical. So this moves us towards what I call a critical value of the column density. Anyone would call it that, actually. It's not an idea that's unique to me. But it appears as though the column density of the order of 10 to the 22 is something of a critical value. And above that column density, the role of the magnetic field in the interstellar medium changes. As we've said before, just moments ago, for lower column densities, lower than 10 to the 22, the magnetic field appears to be roughly constant as a function of increasing column density. But once we reach about 10 to the 22, the magnetic field strength increases as a function of increasing column density. And this diagram here, which was shown by Marc-Antoine yesterday, or one like it, from the Planck data, illustrates that another change that occurs, at least statistically speaking. This is work that is largely the effort of Juan Soler and others, of course, in the Planck collaboration. This is one of those familiar Van Gogh diagrams. And you can see here that in this torus molecular cloud diagram, for higher column densities, the magnetic field tends to be perpendicular to the elongated structures. For lower column densities, it tends to be parallel. The situation, of course, is a statistical one. It's in practice somewhat more complicated than this simple statement would suggest. But nonetheless, again, a column density of 10 to the 22 appears to be a critical point where things change, statistically at least, from magnetic fields lying parallel to elongated features to magnetic fields lying perpendicular. And then also in a diagram shown by Marc-Antoine yesterday as well, also from the Planck data, if you plot percentage linear polarization as a function of increasing column density, you find that for column densities that are greater than 10 to the 22 or so, the percent linear polarization drops drastically. So we can lay out these 3 parameters here, which change when you reach, as a function of increasing column density, when you reach a column density of 10 to the 22. The magnetic field starts to increase at about a column density of about 10 to the 22. That's as a result of the Zeeman observations that have been made over the years. And the Planck data then provide these other 2 changes that occur as you reach a column density of 10 to the 22, the percent linear polarization dropping drastically, and the, statistically speaking at least, orientation of the magnetic field with respect to elongated structures also changing. Now, we can also look at the magnetic field measurements, the Zeeman measurements, as a function of volume density, and as I'm sure almost everyone here knows, Crutcher, again, the name Crutcher comes up a lot, just as the name Heiles does. Crutcher and collaborators undertook an elaborate Bayesian statistical analysis of magnetic field results, Zeeman results, plotted as a function of volume density. So this plot here looks a little bit like the plot I showed you before, but here we plot line of sight magnetic field as a function of volume density rather than all the other plots I've shown you that are a function of column density. And they found that at a volume density of about 300, the magnetic field begins to rise. And you see that here, the lines show a best fit that they obtained from their Bayesian analysis. So we not only have a critical column density of about 10 to the 22, but we have a critical volume density of about 300. So that allows us to consider further the meaning of this. With a critical column density and a critical volume density, that defines a critical scale length, and that critical scale length, the ratio of those 2, column to volume density, is about 10 parsecs, sort of on the order of a GMC or somewhat smaller, actually. But it's interesting that 10 parsecs, that same 10 parsecs, which is the ratio of these 2 observationally determined critical numbers, that dimension of 10 parsecs is also roughly the Jeans length of a gas with a volume density of 300 and a temperature of 50 degrees. Now, another interesting point, which is clearly related, and this is an idea that Chris McKee mentioned to me at a recent conference. The onset of gravitational instability in the galaxy, in the galactic plane at least, will occur when the total galactic midplane pressure, P0, is equal to the gravitational pressure, which is the mean weight of material in a cloud. And so the midplane pressure is known. A value has been determined by Heiles and Crutcher in 1990. We know that, and so if we equate those two pressures and then solve for the column density, it comes out to be approximately 10 to the 22. So that is a further indication that the column density of 10 to the 22 is a critical column density, and the purpose or the reason for that physically is fairly straightforward. The role of the magnetic field in molecular cloud evolution, or cloud evolution in general, changes once self-gravitation becomes important, and that it becomes important, at least statistically, based on the Zeeman effect results. It becomes important at size scales of order 10 parsecs, and for densities of order a few hundred, and for column densities of order 10 to the 22. And at that point, as you consider environments of increasing column density, at that point, things happen. That is to say, the magnetic field begins to rise, the orientation changes, present polarization drops. So that's where we are now in terms of the Zeeman effect. I feel in some sense, a sense of partial satisfaction, having worked both with Carl and Dick and others as well, like Edith, that we've reached a point now where we can make some general statements about the statistical nature of the magnetic field. We have enough data at this stage to say something. And I say that because I remember many years when I worked on this project, and Carl did, and Dick did, and after many years there were times when we didn't have enough data to make any more definitive statements, but now we do. So let's consider briefly in just the last few minutes the future of Zeeman observations. There are a number of initiatives that are possible. Some I've thought of here, well, not just me, of course, but they're obvious ones. Maybe some others that others have not thought about, or at least that I've not thought about, but others have. We're still working, Dick and Edith and I and other collaborators are still working on the CN Zeeman effect using the 30-meter telescope in Spain, the IRAM telescope. And Dick, of course, presented some interesting results yesterday that come from that telescope recently, and the CN Zeeman effect, n equals 2 to 1. So that's a project which we think is worthy of continuation, single dish observations. We'd like, of course, to go to ALMA. There are a lot of problems, Dick mentioned them briefly, a lot of problems at ALMA with circular polarization studies of spectral lines. It's not authorized at this point because there are a number of calibration issues which they have not been able to attack. So we hope at some time in the future, ALMA will allow for obviously high spatial resolution, very sensitive observations of the CN Zeeman effect, so we can probe smaller and smaller scales and look at parameters like the mass to flux ratio on small scales, as well as the increase in, or at least the functional change of magnetic field strength as a function of volume density, and for that matter, column density. So these are two initiatives that I think are very relevant and worthwhile in the future. Then there are other possibilities which are worth mentioning. Tim Robichaud is up to his ears or elbows or whatever part of the body it might be in a Zeeman effect proposal, or project, I should say, in Penticton to continue in some sense the Zeeman effect observations of OHO Mission in the galaxy that began many years ago with Carl and with me. So that's a promising future initiative. And then with larger apertures, such as FAST, it should be possible to observe more H1 and OH absorption Zeeman effects, and therefore increase the statistics from the results that come from Arecibo already. So in short, I think the history of the Zeeman effect has been one rich with disappointment, but also with success. I remember when I was in graduate school, I was reading a review article written by Gerrit Verschuur on the magnetic field, and he had a section, of course, on the Zeeman effect in which he said that the Zeeman effect was a very difficult type of project and was certainly not recommended as a thesis project for an aspiring graduate student. I did not take Verskier's advice, but nonetheless, I think the Zeeman effect has been already now rich in its results, and I think there is a bright future to Zeeman effect observations, and I hope myself to be just a very small part of that future, but others will carry on, obviously, into the future, and the understanding of magnetic fields, I think, will increase dramatically in the next decade or beyond as a result of Zeeman effect measurements and also, of course, other measurements of the magnetic field. Thank you very much.
Okay, we have about 5 minutes for questions for Tom. Let's see, let's begin with Alex.
Okay.
Maybe that's a mistake, I don't know.
I don't know, Alex, thing is, Alex is very shy, so I'm going to try to tease something out of him, okay? Go for it.
I'm very, very shy. I'm not sure that I will be able to ask you this question, but let me breathe and then ask. Okay. I believe that there is another possibility of having the number around 10 to the 22 or several times 10 to the 22.
Let me read your mind. 2 words, reconnection, diffusion.
Yeah, because you do this. And this is, can I think, get a nice transition from the region when we do not have the correlation between magnetic field and density, and when cell gravity becomes more efficient in terms of concentrating matter while there is no time for the connection diffusion to happen. We can discuss this particular number a bit later, because it depends on this injection scale of turbulence and some things which are not so certain, but we can discuss this.
I would like to discuss that. I'm familiar to some extent with that work, I know, and I know that can also be relevant to this 10 to the 22 column density. I didn't mention in my talk for lack of time, and I knew you would bring it up. So it's a very worthwhile idea indeed, and I look forward to talking with you about it.
Okay. Paolo? Can we get a microphone back to Paolo?
So, hi Tom. Can
Hi
you
there.
think of another molecular tracer that can be used for the Zeeman effect? Especially, I'm thinking in ALMA, because CN221 is just 1/6, and we have a lot of more space to probe, especially at high frequencies.
There are other Zeeman tracers. In some cases, ones that have been attempted. CCS, as an example, has a series of transitions. So far, to my knowledge, there have been no successful single dish detections. One of the problems with the Zeeman effect is you go to higher frequency, it becomes more difficult to detect because the splitting in hertz is typically about the same throughout the electromagnetic spectrum. But of course, as you go to higher frequency, the line widths become larger in hertz. So ideally, you'd like to remain as low a possible frequency as possible for sensitivity purposes. But it is certainly conceivable that there are other molecules, but not very many, that could be used. CN seems like a great choice in the sense we already know it's detectable, but the possibility of considering other molecules is certainly one that's relevant. Yeah, that's a good point.
That's yellow. One more question, maybe.
Thank you. There was a paper of Basu, it's regarding this correlation of magnetic field strength and gas density. Correlation of magnetic field and gas density, right?
Oh, yeah, Basu, yeah.
Yeah.
Sure.
He included velocity and correlated n, not with n, but with nu squared, kinetic energy density.
Yes.
And the result was that the correlation was tighter. Mm-hmm. What do you think about it? What's your opinion about this?
That simply means, if I understand correctly, that the magnetic field is more or less an equipartition with the
implication,
turbulence.
yes.
That is to say, the alpha Mach number is approximately equal to 1. Yeah, that makes sense to me, sure, it's good. I mean, that's an interesting result, it's not, it's an interesting result, and it's I'm sure, correct.
Thank you.
Sure.
Okay, great. Let's thank Tom again.